Hello, and welcome to my third video. In this one, I was going to go over a little project I've been working on for the past week and a bit now, that I'd like to call the dual needle problem. A bit of backstory for this problem. I solved the Buffon needle problem a while ago. That was a super fun one to work on. And the dual needle problem is kind of inspired by the Buffon needle problem. I had a whole ton of fun working on the dual needle problem, and I am really excited to share it with you guys. So, before we get into how to solve it, we should probably look at what the problem actually is. Basically, let's say we have two needles and we throw them down randomly. So we have one needle, maybe lands kind of like that, and has a center point right there. And another needle that lands kind of like that, and has a center point right there. Now, assuming that each of these needles has a length of exactly 1 unit, and the distance between them, I'll call that d, d is no greater than, so it's less than or equal to, r units. What is the probability of the two needles intersecting in terms of r? So actually, I encourage you guys to pause it here, just try it on your own, because it is, I don't know, I had a lot of fun doing it. Um, but if you want the solution, I will get into that. So, the first thing that we can look at is, okay, let's say we toss down some needles, like that. And we can always reorient these needles so that one of them is perfectly flat, and we can assume that its coordinates are centered at 0, 0. And when I say its coordinates, I should say the coordinates of the center point. So 0, 0. And we know that its angle, theta 1, equals 0. Now, the second needle, we can say, has coordinates px, py, and we know that 0 is going to be less than or equal to theta, which is going to be less than or equal to pi radians. And now what we've done is we've narrowed it down so we just have to track the position and angle of one of these needles, which simplifies the problem significantly. Now what we want to do is look for intersections, and a great way to find these intersections is by using little systems of equations with some linear functions. So what I mean by that is basically we can define these two needles as lines on a coordinate plane. So I'll call this one L1, I'll call this one L2, and we'll say the line representing L1 is just L1 of x equals 0. Because, of course, it's perfectly flat, so it has a slope of 0, it's located at 0, 0, it's just equal to 0, kind of no matter the x position. L2 is a little bit more complicated. We have to use a little bit of trig for this, but it's not too bad. We just do tangent of theta to find our slope, then multiply that by x minus px, then add py onto that, and that will give us the line of L2. To make this a little bit visual, L2 will look something kind of like that, except it'll go shooting off to infinity, of course. L1 will look something just kind of like that. Oh, whoa, that missed L1 massively. There we go. L1 will look something a little bit more like that. And of course, both of those will go off infinitely. Now, I know I'm saying that they go off infinitely, and you might think that's a little weird seeing as the needles obviously don't go off infinitely. We will address that later when we start setting up our inequalities. I'll show how that is addressed. But for now, let's find our intersection point. Visually, it looks like our intersection point, which I will call I, is right about there. Because you can see if we extend this line out and extend this line out, looks like they kind of intersect right about there, right? And we can calculate I by setting L1 of x equal to L 2 of x. So, if we just substitute in these definitions, we get L2 tan theta times x minus px plus py equals 0, which is just L1 of x. We can then solve for x. Let's factor that tan theta in. X minus... Right? And then we can move all of those n terms off on the other side, so we get tan theta x equals, let's see, tan theta px minus py. Then dividing both sides by tangent, we get the x position of our intersection point is equal to tan theta px minus py divided by tan theta. And there you go. That is the x position of I that I've labeled there. Now, we actually know the y position of I. Because L1 is always equal to 0, we know that the y value of I is also always going to be 0, because if anything intersects with L1, it intersects when y equals 0. So we can write out that I, our intersection point, equals tan theta px minus py divided by tan theta. That's our x position. And then our y position is just 0, which makes it nice and easy. So now we should probably start setting up our inequalities, and this is where I will address the finite length of our needles. So there's a couple of rules for what defines an intersection between these needles. The first is that the distance from our first needle's center point to our intersection point has to be less than 0.5. That is because our needle has a total length of 1. So this distance right here is going to be 0.5. 0.5. If the distance from this center point to I is less than 0.5, we know that I rests somewhere along this line right here. Right? Now we also know that I's distance from our second center point here also has to be less than 0.5, because that means that I will rest somewhere across this line. And if both of those things are true, we have ourselves an intersection. So let's write out the mathematics for that, shall we? So the distance from our first center to I is going to be equal to ix squared plus iy squared, and the square root of all of that. That's our distance, and we know that that has to be less than or equal to 0.5. And that's just using the distance formula. Now, we also know that the distance between our second center point and I also has to be less than 0.5. And we can write that out as, there we go, ix minus px squared plus iy minus py squared has to be less than or equal to 0.5. If both of these things are true, we have ourselves an intersection point. And we're going to go visualize this in Desmos, because visualizing these problems really, really helps. So here we have a visualization of those inequalities graphed in Desmos 3D graphing calculator. I know a lot of people don't actually know about Desmos's 3D mode, But it is pretty cool. I strongly recommend looking at it. You just type in Desmos 3D graphing calculator, top result. It's pretty awesome. But anyways, this is a visualization of those inequalities, where x and y represent the position of our second needle, and z represents the angle. Now, this volume right here is every single combination of those three variables that results in an intersection. And it's defined by those inequalities that we found previously. So, for example, if we just look at this top down, so ignoring the z for now, if our second needle, if its center position is outside of this kind of oval shape right here, well, not really an oval, but that shape right there, then it cannot intersect with our central needle, because it's just too far away. However, if it is within that oval, then this z will tell us all of the angles that allow it to intersect with our central needle. So you can see if it's right on the very edge, there's only actually two angles that will allow it to intersect. This bottom is 0, this top is pi. And then as we move closer, there's more and more angles, and we kind of move around. You can see there's lots and lots of angles. If we're right at the very middle there, then obviously any angle will work, because our center points are aligned. And it's kind of a handy little visualization. Now, to find the probability of these two needles intersecting, we can find the volume of this shape and divide it by every single possible combination, which is defined by this volume. This volume kind of depends on r, where r is the maximum distance between the center points. It's currently, I'm assuming, an r of 2, but it can really be anything, and you can see as we rescale r, that cylinder will change. And what this is saying is the position of our second needle's distance from that central needle can be anywhere within this circle, and it can be at any angle between 0 and pi. So it's just every single possible combination. This volume right here is all the ones that actually work. So the volume of that shape divided by the volume of this whole cylinder will give us that probability. Now, to be honest, finding the volume of this shape scared me a little bit. I was looking at it and thought, oh, there's going to be some potentially gnarly multivariable calculus stuff in there. I was trying to define the sides with functions, so then I could maybe integrate them, and it all got a little crazy and a little gnarly. However, after staring at it for probably way too long, I realized what we can do is get this shape and split it up. So now we have two shapes. Now if we bring that side over here, these fit together perfectly, and you can see as we zoom in, sure enough, fits together. And that kind of makes sense when you think about the symmetry of the situation. Now this shape has an identical volume to our previous shape, but it is much easier to find the volume of this shape, especially since we can actually define these sides just by a few sinusoids, like so, and then we can just integrate this. So to find this surface area of one face, we can do the integral from 0 to pi of 1/2 sine of x dx. That will find half of this surface area. So multiplying by that by 2 will find our total surface area. Then all we have to do is multiply this by the depth. And you can see we actually just have a depth of 1. It might be a little easier if I turn off those. We just have a depth of 1. So this is literally just 2 times 1. And that's the volume of our shape. It's just 2. And it's kind of cool to see a shape that looks like this, and to just rearrange it so the answer becomes a lot simpler. That was really fun. That realization took me a long time to figure out. I got actually quite excited when I figured that out, but it was a quiet excitement because I was in the library surrounded by other people studying. But yeah, and it simplifies the process down a lot. So we know the volume of the shape is 2. Now all we have to do is find the volume of this whole cylinder, Well, the cylinder's volume is just the base multiplied by the height, or the surface area of the base, I should say, multiplied by the height. So the surface area of the base is just going to be pi r squared, and then that multiplied by the height is just pi, so we can just multiply that by pi, which then simplifies down to pi squared. And then the volume of our solution set divided by our total volume of all the different possibilities is just 2 divided by pi squared r squared. And there you go. That is the probability of those two needles intersecting, assuming a distance of r. And you can see as we change r, that number will change. So as r gets bigger, those needles can land farther away, and this will get super, super small. As it gets closer and... oh, that's the wrong one. That should be 0. As it gets closer and closer together, you can see that number get bigger because the needles are landing closer. And yeah, it's a super satisfying, simple answer right at the very end. If you've done the Buffon needle problem, you can kind of see this answer's relation to the answer of the Buffon needle problem. And yeah, that is it. So thank you guys for watching. I hope you enjoyed this problem as much as I did. I had a lot of fun working on this. So yeah, I hope to see you guys next time.